the fourth day of the week. So yeah, okay, let's get started.
Sure, thanks. Thanks everyone for being here again. So the way that yesterday ended was with stating this Zilbert trichotomy and the weak trichotomy theorem. So I'll show them again. You see it moving, right? Yeah, it looks like you see it moving. Okay, so recall what we're trying to do. We have our strongly minimal structure, and what we're trying to do is break into cases according to how big are the families of plane curves that occur in the structure. So we're looking at families of curves in the plane m squared, and we're measuring the size of those families using the dimension notion. Okay, and the most effective way of doing that, wherever I wrote it, is with taking the canonical base. So here we go. So a plane curve. So we take the canonical base of a stationary non-trivial plane curve as a number that codes how big of a family do we have. So what's like however big the canonical base of a stationary non-trivial plane curve can be, that is the largest size of a family of plane curves that you can find. And the theorem, the weak trichotomy theorem, says if you look at all of those sizes of families and you form a set out of them, then there's basically three options for the set. It's either just 0 or 0, 1, or as soon as it has a 2 or bigger, it becomes unbounded. Okay, and then the other part of the theorem is that if the structure is totally categorical, only the first two can happen. So it's always bounded, and in fact, it's always bounded by just 1. This theorem, it's really two theorems. I would love to say something about the proof, but I'm going to skip it for now just because I want to get as much as possible to other stuff today. So basically, if we finish early tomorrow, I'll come back to this. But for now, I'm just going to leave that as a black box. And then this becomes the trichotomies. There's three cases. Three cases are called. Everything okay? Uh, are you able to mute whoever is making the noise? Oh, okay. Thank you. Okay, so these three cases become the trichotomy, and they're called trivial, and then non-trivial locally modular, and then non-locally modular. And again, the reason for that is that for historical reasons, the first two cases union together were called locally modular. Okay. And then, well, roughly speaking, what we want to say is that trivial things look like pure sets, non-trivial locally modular things look like vector spaces, and then we won't have time to say this, but what turns out to be the case often is that non-locally modular things look like fields. Okay, so what for today, okay, so this is like the plan for today, is as much as possible, start to prove these 1 and 2 characterizations. So the trivial looks like a pure set, and non-trivial locally modular looks like a vector space. And largely, in the case of totally categorical case. And the reason for that is that you can get the strongest statements there. But we're going to prove, I mean, we'll stick to more general statements, and then we'll just, after having more general statements, we'll say, if you want to see this look really clean, look in the totally categorical case because it's cleaner there. Okay, so that's sort of the summary. Now, I think I said something in the notes along the lines of like, if you take something which is on one of the levels, so like, you have like 3 levels in the trichotomy. So if you take something which is on one of the levels, and then you like add some constants to the language, say, then you don't leave that level. You have to stay at the same level. If you remove some constants, you stay in the same level. If you like quotient by an equivalence relation with finite classes, you stay on the same level, etc. So there's some things in the notes that are like, basically, it's hard to make things change levels. You have to really switch to a genuinely different sort of object to switch levels. And I'm just gonna skip that for now. So I'll point it out when it comes up, but otherwise I'll skip it for now. So in the notes, I'm now moving on to what's subsection 6.5. Okay, so I'm going to jump ahead a little bit. Okay, so next thing. So we want to, so next goal is characterize, so equivalent characterizations which are going to be a little bit more helpful of trivial and also of locally modular. By the way, if you want to know, the word modular comes from module, so it's supposed to be like a vector space. It was originally called modular for like coming from like a module, and then locally it was somehow like it's not a module yet, but it's like if you localize it becomes a module. But that's related to other things, and the you know we don't we just still call it that because it originally was. So okay. Equivalent characterizations, which will be stronger statements that are going to be more helpful when we start proving things. So let's start with trivial. So lemma, which I'm not going to prove, but so M is trivial if and only of the following. And this is actually more commonly the definition of trivial. So for all A subset of M and let's say B in M, if B is in ACL of A, then B is in the ACL of some element of A. Okay, so in other words, we always know that being in the ACL of a set, you can restrict it to a finite subset. If you're in the ACL of A, then you're in the ACL of some finite subset of A. We're saying you're actually in the ACL of a single point. Right. So for instance, like here's a reason that, I mean, we know this for other reasons, but here's one reason that C plus times is not trivial is because, something like you take, assuming that pi and e are independent, I believe that's an open problem, but I'm going to act like they are. So pi plus e is in the ACL of pi e, but it's not in the ACL of pi, and it's not in the ACL of e, and that's enough to say that it's not trivial. Okay, so for if it was trivial, then because pi plus e is in the ACL of pi and e, it would have to be in the ACL of one of the two. Okay. The proof is I'm going to skip it. It's an exercise. Okay, this proof is an exercise. I think it's not too crazy. Okay, the idea is like, well, you can reduce it down to like one point is in the ACL of some independent set of coordinates, and you want to show it's in the ACL of one of them, and then you sort of add parameters for all but one so that what's left is a plane curve, and then you say, well, that plane curve has to have a zero-dimensional canonical base and something like that. But again, I'll skip that for now. And I want to get to the locally modular characterization. So here is how we characterize locally modular. There's going to be multiple ways of doing it. So this is locally modular characterizations. And the idea of what I want to get across here is, so locally modular is a restriction on the plane. So we're saying if you have a family of curves in the plane, then it's small. So the slogan for locally modular is you have only one-dimensional families of plane curves. No more than one-dimensional families of plane curves. And that's a specific statement. It's saying for one-dimensional subsets of a very specific set M squared, you have a bound on what the families are. And so you might just, I mean, it's a very natural thing to say, what about like, are there bounds on families of subsets of M to the 4 or something like that? Why do we care so much about M squared? And the fact is that our knowledge of M squared coming from local modularity actually exerts a complete control over subsets of M to the N for every N, and even more general than that. So that's what this fact is going to say. And There's another way of saying it in higher stability language is that locally modular is equivalent to something called one-based. So I'll say why it's called one-based. So, okay, so assume M is locally modular. Then, so locally modular says if you have a stationary almost equality class of dimension 1 in the plane, then you have a bound of 1 on its canonical base. So something similar. So let, where did I write this down? So let X be in M to the N, stationary, of dimension D. Then we have what I would say is the most natural bound possible for the dimension of the canonical base. So dimension of CB of the class X is at most N minus D. So if N was 2 and D was 1, it would be the plane curve case, and then you'd be saying 2 minus 1, which is 1, and that's the definition of local modularity, but in general, it's N minus D. And this should make sense, because if you have, like, say you're in 10-dimensional space and you have a family of surfaces of 2-dimensional things, local modularity is saying that you can have 8-dimensional as any of them. Right? So it's like if you have 8-dimensional family of 2-dimensional things, then it covers in total dimension 10. So local modularity is saying that natural bound always exists. So example, so ACF is not locally modular. And well, we've already seen this, but because you can take the collection of degree D varieties if you want in M to the N is arbitrarily large. So you can take like a family of stationary sets in M to the N, which is arbitrarily large. And whereas local modularity says, no, it's really bounded by N minus the dimension of each one. Okay. So great. So that's saying that in M to the N, you have a bound on how big of a family you can have. But you can say more. So slightly more general version. Okay, let's say that Y be stationary, a definable, and of dimension D. So what I'm going to do is make the same statement, sorry, not of dimension D, of dimension N. I'm going to make the same statement, but I'm going to replace M to the N with Y. So now it's instead of inside M to the N, it's inside any ambient thing. And let X be inside Y, stationary of dimension D. Then dimension of canonical base of X over A is at most N minus D. Okay, so it's the same thing, but happening inside the ambient space Y. And in order to do that, we have to add a set of parameters to make Y be zero definable. So it's definable over A. You don't have to do that in the previous thing because M to the N is zero definable. But again, it's saying that inside an n-dimensional set, any family of d-dimensional sets has size at most N minus D. Okay, and then 3 is the cleanest statement, but the one that you have to think about the most. Right, so for all A in MEQ and all A contained in MEQ, the canonical base of A over A is in the ACL of A. Okay, so you can see it's a very clean statement, but like, why is that the same thing, right? So this is the same thing. So why is this the same? Okay, so let's let C be the canonical base Okay, sorry. So for instance, let's say x in m to the n stationary of dimension d. And C is the canonical base. And then we take some generic. All right, so take A in okay, well, I haven't said that. So okay, I should say something. Because C is the canonical base of X, there is some definable set almost equal to X, which is definable over C. So Y is from the class C definable, and then let's take A and Y to be generic over C. All right, so I have my D-dimensional set, and I can assume after tweaking it a little bit that it's definable over the canonical base C, and then take a generic point. Okay, so let's compute the dimension of AC. So dimension of AC is now, well, two ways. So first way we'll do it, so there's another double counting thing. So first way we'll do dimension of A over C plus dimension of C. This is going to be D. I suppose this is an exercise that I skipped again. I'll state something clean after this. Because the set Y is a D-dimensional class, it turns out dimension of A over C is D. But I'll state that after I finish this. And then plus the dimension of C. Okay. On the other hand, if we break it up the other way, it's the dimension of C over A plus the dimension of A. And A comes from this ambient space, right? So the dimension of A you can bound. It's at most n because it's an m to the n. So is at most dimension of C over A plus n. Right? And this expression up here, right. So, okay. So now you have D plus dimension of C is at most dimension of C over A plus n. Right? And so if we say that, so if C is an ACL of A, that's the same thing as saying that this term right here doesn't exist. So that's the same thing as saying that dim C is at most n minus d. Okay, which is the original. So there's some so that's why they're the same. Okay, it just comes from computing the dimensions. But really think of it like this. Think of it as you have like an 8-dimensional family of 2-dimensional sets inside m to the 10. Then they kind of look like they're disjoint, right? The expectation is that those sets are now disjoint. And what that means is that if you know one point on one of the sets, it should determine which set you're looking at, which is exactly what it's saying. Like this C is in ACL of A. It's saying knowing one point basically tells you which set you're on. Okay, so these are all equivalent, and they're all equivalent to local modularity. This number 3 is like the most helpful, but again, it's the most abstract. And number 3 is called one-based. So this condition 3 is in abstract stability, it's called one-based. And it's called one-based because it says knowing one point approximately determines a set. So it determines a stationary set. Right, in the sense that the canonical base is algebraic over the one point. So it's kind of like, yes, one base, one point is enough. Okay. So the one thing I skipped, so so something we skipped. And it was an exercise, and I should probably state it now. So suppose that I started to say this yesterday, and then I stopped, and there was an awkward pause, and I was like, should I say this or should I not? And then I said, I'm going to do this after canonical bases, and this is what this is. So suppose that X is stationary. I'll say that I'll put a class thing around it. So suppose that class of X is stationary almost equality class. with canonical base C. Then the set of generic points of the class over C is well defined. And determines a complete type over C. And in order for that to make sense, you should first understand why it doesn't initially look like it makes sense, right? So a generic point of this class over C, we're used to taking generic points of definable sets. So you can have a generic point of a definable set, but I'm talking about a generic point of an almost equality class of definable sets, which is a little bit funny because, you know, the different sets are different, right? So a generic point of like a whole bunch of different sets at the same time, right? And so what I'm really saying is there is some member of this class which is definable over C. And if you look at different members of the class which are definable over C, any two of them will have the same generics over C because they're almost equal. And then if you take the set of those generics, that determines a complete type over C. Right? And so kind of going along with this, if A is generic in the class over C, then dimension of A over C is whatever the dimension of X is, right, as is expected, and C is equal now to the canonical base of A over C. As you get this sort of nice picture. All right, so I was kind of using this above here when I said here the dimension of A over C is just D here. I was using that. Okay, so this is the characterization of local modularity, and it's a bit tricky to prove. The quickest proof that I know of involves coming up with with yet another equivalent condition, which is not very obvious at all, and then proving that equivalent condition by induction. And I sketch how to do that in the exercises. But I'm not going to do it now. But just understand that if you know a restriction on plane curves, it gives you a restriction on like any type of definable set. There's not that many of any configuration of definable sets present. Okay, so that's our equivalent conditions, and now let's start proving things. So we want to show that trivial kind of gives you a pure set, and well, locally modular non-trivial gives you a vector space. And so let's just do one of those now. Okay, so let's call this a theorem. Suppose M is trivial, and like I said, I'm gonna look in the totally categorical case. If you don't want to assume totally categorical, then what you need to do to make sense of this is to define something called the associated geometry. And we might do that if we have more time tomorrow, but I'm not going to do it now. And then the associated geometry is a pure set, but that's not a definable object, so it's kind of funny. I want to stick to something definable, so I'm going to assume totally categorical, and then everything works really well. Okay, so there is a definable equivalence relation. So in fact, a zero definable equivalence relation. E on M with all classes are finite. So it's a fairly harmless equivalence relation. You're not changing M by much when you mod by it because all the classes are finite, so that M mod E is a pure set. And this means that the definable subsets of, so M mod E exists in MEQ, and so the definable subsets of M mod E to the N are just definable from equality.
So in mod E, you might have like parameters named, right? At the definable, doesn't really matter for what you're saying.
Can you, I can't hear you that well. Can you say that again?
Oh, sorry. In mod E, you might have parameters, you might know about certain parameters, right?
Yes, correct. Yeah.
Okay.
Yeah, you can do it. Yeah, if you want it to be literally the language, I mean, if you want these zero definable sets to be zero definable in the pure set, so the parameters match, then you might have to delete finitely many points from M as well. If you just care about the collection of all definable sets over all parameters matching, you can leave it as M mod E. Okay. So let's prove this. So what is E? So E is going to be, let E be X and Y. So it's the equivalence relation on X and Y. X and Y are inner algebraic. Okay. So this might seem like you can't do that. That's not defined, but it is, because totally categorical just lets you do that. So this is definable. E is zero definable because of particularly the Aleph zero categoricity. So Aleph zero categoricity says that there's only finitely many zero definable sets in M squared. And so in particular, there's only finitely many formulas that could possibly witness the inner algebraicity of 2 points. So you can define 2 points are inner algebraic by just saying, here's all the reasons that they could be inner algebraic, and our formula just says one of these holds. Yeah. So saying that they're inner algebraic is just some big finite disjunction. If you don't assume Aleph zero categoricity, you still look at M mod E. It's just that M mod E is not definable anymore. It's the associated geometry. You have to make sense of that. Okay. So we show that M mod E is a pure set. So let X be in M mod E to the n. So okay, let me before I start. So let's just replace M with M mod E. Okay, let's for convenience. For convenience, let's replace M with M mod E, because I don't really want to have to write the mod E every time. And so therefore we assume from now on that inner algebraic points are equal. That's what that means. So if 2 points are inner algebraic, they have to be equal. Okay. That's an easy exercise to check that if you mod by E, then in the resulting thing, inner algebraic points are equal. And so now let X be in M to the n definable. And we want to show that X is definable from equality. Okay, so we will do this. We work by induction on the dimension. So we assume that we've covered all the previous dimensions. So notice that the case that X is finite, so X finite is clear, because every finite set's definable from equality. And we assume that all the smaller dimensions are done, and now that X is, say, dimension at least 1, so assume that perhaps this isn't necessary, but we'll do it. So assume that the dimension of X is D, which is at least 1, say. And then the next thing is we apply the stationary decomposition. So write X as a union of stationary pieces, of stationary components. And handle each separately. So that is, we're going to do each of the stationary components separately. And if we can show that each one is definable from equality, well, then X is just a disjunction of a bunch of formulas in the language of equality. So X is still definable in the language of equality. And so thus, we assume X is stationary. So thus, assume X is stationary. And let's fix a set defining it. So we'll say that X is a definable. Okay, so why did I want to do that? So at this point, I'm going to sort of identify X with its generic type. So I wanted to reduce to something about a type. Now I've done that. So the way to do that is to take a generic point. So let A be generic, and so A is in M to the n, so we'll give the coordinates names. So I'll write the coordinates as A1 through AN. Generic in X over A. Now, when you do this, when you're trying to say something about the definable set X, and you do it by taking a generic point, what we're going to do is somehow say that the type of A1, AN is coming from equality. What that will tell us is that almost all of X is coming from equality somehow. And then we'll just say, well, anything that's different is smaller dimension, and we use induction. So this is the general structure. Okay, so we have this thing A, and we can reorder the coordinates, and that won't affect anything. So let's just assume that we have a basis consisting of the first D. So we may assume that A1 through AD is a basis over A. Okay. And now I'm going to try to describe the whole type of the whole tuple just using equality. So because this is a basis, so if I is bigger than D, then AI is going to be algebraic because it's a basis. So it's algebraic particularly over A together with A1 through AD. Okay. Well, we're assuming trivial, right? So since we're assuming trivial, we can use this fact that says, therefore, AI is algebraic over one of the points. So either AI is algebraic over, well, okay, let's not say it that way. So let's say there is some C where either C is in A or C is one of these basis elements where A is algebraic over C. AI is algebraic over C. Okay, so A is algebraic over a single point, and that single point is either coming from A or it's one of the basis elements. Okay. Right, so now we have two cases. So two cases. Case one, C is in ACL of A. Well, then so is A, I. And we're going to say, in that case, we'll know what to do. I'll say what to do in a minute. The other case is that C is not in ACL of A. Well, now we have this exchange lemma, or just, we use additivity. So AI is algebraic over C. Oh, sorry, I should have said, no, yeah, this is right. What am I doing? I think I wrote something wrong. Yeah, I did. I wrote something wrong. Okay. Well, we can work with this. We can just keep going. So suppose C is not algebraic over A. Well, then we look at the point A. So maybe we have three cases. So A in ACLA. Well, then same as the previous. So yeah, we say we know what to do if AI is ACLA, which I'll say that we do in a second. And then lastly, well, what happens if C is not in ACLA and neither is AI? And now we use the exchange lemma. So here we have 2 points, AI and C. They're both singletons. Neither one is algebraic over A. And there's a dependence between them because AI is algebraic over C. Well, then C is going to also have to be algebraic over AI. So in this case, they're inner algebraic.
Wait, aren't we assuming that we're in the trivial case? We made inner algebraicity be equality, right?
Yes, that's the next thing I'm going to say.
Well, so we could just say that AI is either an element of A or it's one of the A1 through AD, right?
Yeah, that's what I was trying to say. Okay, so here C equals AI. And okay, so the conclusion, well then C was either in A or was one of the A1 through AD. So in any case, one of 2 things has to happen. So this is what I was trying to say, and I went a roundabout way. So one of 2 things has to happen. One is AI is in ACLA, or AI is equal to one of the previous. Okay, and that's true for every one of the remaining elements. So for any I bigger than D, AI is either in ACLA or it's one of the basis elements. Okay, so now take a formula saying that. So now take formula phi of x over ACLA. It has to be over ACLA because we have this case that it could be an ACLA, expressing that. Oh, I'm sorry, not phi of x. It's going to be phi of the whole thing. So phi of x bar, yeah, over ACLA, expressing that each xi is in ACLA is equal to some particular element of ACLA or is equal to some basis element. So for all I bigger than D. So in other words, all of these facts that are true of the tuple A, where each of the end coordinates is equal to a particular point, just write that down in a formula, and you get a formula over ACLA. Okay? So then our point A satisfies phi. And well, A is still generic in X, so A is still generic in X over ACLA. Why is that? Because it was generic over A, and when you add the ACL of A, it doesn't decrease the dimension, so it's still generic. Okay, and so we found a generic point of X which satisfies phi. So a generic of X satisfies phi. Well, X is stationary. So in fact, all the generics have the same type. Otherwise, you could break it into 2 generic pieces. So in fact, what this means is that all generics of X satisfy phi. And well, that means that X is almost contained in phi. Great. Well, but in fact, that's going to mean that they're almost equal. Okay, because phi has the same dimension. So note that phi, so phi is just some formula which is saying I have D free choices, and then each other thing is equal to a specific element. All right, so phi is just projects bijectively to the first D coordinates because each of the final D coordinates is entirely determined to m to the D. And so that's going to mean that phi also is also defining a stationary D-dimensional set. It's stationary and dimension phi is D. And now I have 2 sets, they're both stationary, they're both dimension D, and one of them is almost contained in the other, and that means they're almost equal. Okay, so X is almost equal to just the solution set of phi. Great. Well, now phi is definable over equality. And so now I can break x into, now we write x as a Boolean combination of, well, phi and the difference. So x minus phi and phi minus x. So this is just the set of elements of x that are not satisfying phi, the set of solutions of phi that are not in x. And all of these are definable from equality. Why? Well, for phi, it's because it's very literally, it's just a formula and it's using only equality. For the other two, it's by induction. So they have smaller dimension. Because x is almost equal to the solution set of phi, the differences are smaller. Okay, and then so is x. Okay. So that's that proof. So I'll stop. I mean, that might have been a lot, but the reason I did, I think it's when you write it down, it's not so crazy, but maybe when you see it the first time, it's a lot to take in. So I did this because it's a warm up for the later case. So the locally modular case is going to be more complicated, but following a very similar outline. So any questions so far? Again, the strategy is you're trying to show that every definable set is definable from equality or what will later be from a vector space. And we do it by induction on dimension. You can assume the set stationary. Then you look at a generic point and you sort of look at the dependencies between the coordinates and you show that that's coming from equality or later a vector space. And then you extract some equality definable set, which was our phi. Later, it'll be a vector space definable set so that the generic point of x satisfies that, and then those two become almost equal, and then you take the rest by induction. Okay. Okay, so now we'll go on to the locally modular case. So that's going to conclude our section 6, and now we go on to section 7, which is the most difficult of all the sections. Okay. So this is the non-trivial locally modular case. Also called, for us, the group configuration theorem. So it's not the full group configuration theorem, but it's a significant case, and it gives basically the idea of the full group configuration theorem. Okay, so it's going to be similar. So in the trivial case, what we did is we first have this lemma that I didn't prove that says, here's another characterization of trivial. Trivial things have to like look in a certain way, and then going from that, we built some in the totally categorical case, we built something much more specific, which was literally a pure set. I can't find that, so I'm just going to go back. So in the locally modular case is going to be similar. So the first step, which is very, very much the main point, is that we're going to build a group. It's going to be an abelian group in the structure, but we're not going to assume totally categorical there. So, and that's kind of the point, is that there's a group construction theorem that works for any non-trivial locally modular strongly minimal set. So just assuming this, we'll build a group. We'll analyze the group, still not assuming totally categorical. And then at the very end, we'll say, no, if it's totally categorical, then we can do this induction on dimension proof and say that actually we have an exact vector space. Okay, but for now, so throughout this section 7, so we just fix M. Again, it's still uncountable saturated, strongly minimal, and now it's going to be non-trivial and locally modular. Okay, and then the big goal is to find a strongly minimal definable group in MEQ. Okay, now what I mean by that, so a definable group, I mean that there's gonna be a group and its underlying set is gonna be definable and strongly minimal. And then the group operation is also definable. So that's the big goal. Okay. So how? So here, there's a main I'll go to a new page for this. A main definition of the object that we'll use to build a group. So the thing that we're going to use, I'm going to call it the germ groupoid. No one else calls it this. This is not really a thing that other people consider, but I think it's a really useful way of packaging it. So we're just going to do it. So we will use the following thing. So the germ groupoid of M is the category. It's a groupoid. So if you know what a groupoid is, it's a groupoid. If you don't know what a groupoid is, it's a category. As follows. So defined as follows.
Sorry, there was a question about in the proof. Sorry to interrupt.
Yeah.
There's a question in the proof of theorem 6.24. Is the formula phi eventually defined over a canonical base of A1 through AD over A? You can see in the chat this question.
So 6.24, I assume that's what we were just doing. Yeah, okay. Is the formula phi eventually defined over the canonical base? Yeah, I believe so. Yeah. Yeah, phi, I mean, yeah, because what is phi? At the end of the day, phi is a formula that almost isolates the type of A1 through AD over the canonical base. So yes, I think that's true. Maybe there's a way to do the proof shorter that way. Okay. All right, so this germ groupoid, so it's a category defined as follows. So normally people use the word germ, they just don't use the word groupoid because they don't consider the whole thing. I prefer to consider the whole thing. So the objects of the category are strongly minimal sets up to almost equality. So our almost equality classes of strongly minimal sets in MEQ. Okay, so they're almost equality classes of stationary definable sets in MEQ that have dimension 1. And then the morphisms. So if I have C and D are objects, and I look at what are the morphisms from C to D, well, they're almost equality classes as well of bijections, so of definable bijections. X to Y, where X comes from C and Y comes from D. Right, so we're taking, it's basically saying, okay, C and D are these almost equality classes, and then the morphisms are just definable bijections between C and D. Except that doesn't make sense because C and D are not sets, they're almost equality classes. So you also have to take the morphisms up to almost equality. Right, so they're bijections between members of C and D viewed up to almost equality. Okay. And notice, so maybe we should just notice that such a bijection, so a morphism, such a morphism is also stationary. Right, so all the stuff we've developed about canonical bases, they apply there too. Why is it stationary? Because for instance, the graph of the bijection is itself in definable bijection with the domain. So if the domain is stationary, then so is the graph. So in fact, the graph is also strongly minimal. So the morphisms are strongly minimal sets as well. Okay. Yeah, so this is this germ groupoid, and there's an exercise in the notes that basically just says verify this is a thing, right? So check this is well defined. So this makes sense. whatever that means to you, to be convinced that it makes sense. So check that it's well defined, and make sense of almost equality classes of morphisms, check that they're strongly minimal, etc. Okay. Now, so this is this groupoid. By the way, a groupoid in general, if you don't know, a groupoid is a category where every object is invertible, right? So it's like a group, except that, well, an element can go between two different objects. It doesn't always have to go from an object to itself. That's the idea of a groupoid. This is a groupoid, so that's part of the exercise. Check that it's a groupoid. Yeah, and they're called germs because they're viewed up to something. So they're viewed up to almost equality. Okay, now this is not definable. So the germ groupoid is not a definable thing. It's not definable because there could be a whole bunch of different formulas that define strongly minimal sets, and there could be a whole bunch of formulas that define bijections between strongly minimal sets, and we can't quantify over all the formulas in the language. This is not a definable object, but what we're going to say is that, like, it's close enough, right? It's close enough to being definable that we can work with the objects and morphisms in a sort of definable way. And at the end of the day, what we'll say is that there's enough morphisms that can be uniformly talked about definably that we'll be able to get a group out of this thing. Okay, so, but well, we can pretend that every individual object and morphism is an actual element. So, well, we can view objects and morphisms as elements. And we can talk about them definably. We just can't talk about the entire germ groupoid as a definable set. We can talk about individual objects and morphisms. And why? Well, we have canonical bases. So with canonical bases. Okay. So for instance, like, here's something I might do. So the notation, so let's say that if F from C to D is a morphism, then the notation dim F over CD makes sense. What does that mean? It just means C is a strongly minimal almost equality class, D is a strongly minimal almost equality class, F is a strongly minimal almost equality class. And so you just replace each point with its canonical base. So it means it's a shorthand for dim of CB of F over CB of C with CB of D. Right, but we just don't want to write all that. And what I just wrote is like the whole point of canonical bases, right? It's no matter how complicated it might seem, what they do is they just let you talk about almost equality classes like they're elements in the universe, and that's exactly what we're doing. So we're just saying we can talk about the dimension of F because it's an almost equality class and it has a code, which is the canonical base, and so then we just talk about that. So I'm just going to totally pretend that the elements, that the objects and morphisms are actual elements of MEQ, and I'm going to talk about them like they're elements of MEQ. The whole time I'm doing that with canonical bases. So that's the underlying trick that's being done. Right. And we can talk about definable sets of morphisms. So we can talk about definable sets of morphisms C to D. What does that mean? Well, you just take a definable set of functions and then you mod it by almost equality. So an A definable set of morphisms C to D is just the image after modding by almost equality of an A definable set of bijections say x to y, where x is in C and y is in D. Okay, that's all it means. So I'm trying to convey the point that we can really do a lot of work while pretending that everything in the germ groupoid is definable, even if the entire thing is not. Like pieces of it are. And then, okay, what was the last thing I was going to say here? Right. So composition is definable. So composition, I'll just add this as another point in my list. Composition is definable. So what does that mean? It means that if you have objects C, D, E, right, and then you have F is a set of morphisms from C to D, and say G is a set of morphisms from D to E, and H is a set of morphisms from C to E. Right. So given all of this, all definable sets of morphisms, then the set of FGH, where H equals G composed with F, is also definable over no additional parameters. Right. So if this is A definable, then this is A definable. That's worth checking. So that's listed as an exercise. You should see why that happens. So why is it that you can definably say when two morphisms compose to another one? Because again, these are not sets. It's not just literal composition of functions. It's all done up to almost equality. Right. So the formula that says H equals G composed with F is going to be something like for any members of the classes H, G, and F, there are infinitely many solutions to this one composed with this and equals this one. It's going to say something like that. Okay. But nevertheless, so composition is definable. And that's basically the preamble. And throughout the main input of local modularity. So we're assuming local modularity. What's local modularity going to do for this? Well, the main input of local modularity, and this is again listed as an exercise, is that if F is a morphism from C to D, it's now we can give it a very clean statement. So if F is a morphism from C to D, then the dimension of F over CD is at most 1. That's local modularity said cleanly. Okay. It's listed as an exercise. I can sort of say why. It's because if you have C and D, so C is a canonical base for some strongly minimal thing, and D is a canonical base for another strongly minimal thing, and F is a canonical base living inside the product of those two things. Right. So it's basically like say that X is in the class C, Y is in the class D, and Z is in the class F. Then what you basically have is Z is a curve in X times Y. Right, and the dimension of Z is 1, and the dimension of X times Y is 2. And then local modularity tells you that the dimension of the canonical base of Z over the canonical base of X times Y is at most 2 minus 1. Okay. There's a fancy way of saying this is like we have a plane. So we have morphisms from C to D live in like the CD plane, and the CD plane can have at most a one-dimensional collection of morphisms, which is exactly saying dimension of F over CD is at most 1. Okay. So that's the preamble. So this is everything we've said so far, but now converted to the language of the germ groupoid. So let's jump into it. So we want to show that there is a definable group of morphisms from a point to itself. So we will show, so the goal is that there exists a strongly minimal, definable group of morphisms from C to C for some C. Okay, and I said in the notes, by the way, I'm from this point on, I'm trying to reserve the letters C and D for classes and X and Y for definable sets belonging to those classes. Hopefully that's helpful. Okay, how do we do it? So this is in 2 steps. So step 1 is just build any collection of morphisms, build any infinite definable set of morphisms. Surprisingly difficult to do between any 2 objects. That's step 1. Just find some infinite collection of morphisms between 2 objects. Okay, and then step 2 is refine into a group. Okay, and this step 1 is going to be the hardest thing we do in the whole class. This is the hardest thing of the week. And then this is going to be much easier. Okay, so this step 1 is quite crazy. It's not crazy. I mean, it's like a page or 2 pages. It's just that, I mean, I think almost everything that I'm talking about, I feel like I have a good enough grip on. I'm like, this all makes sense, right? I've studied this enough, it makes sense. This one still does not make sense to me. And I'm just gonna say this, the construction of an infinite family of morphisms has never made sense to me. So, right. So some magic trick of Hrshovsky. So let me sketch how we do it. So sketch of how to find an infinite collection of morphisms. So an infinite definable set of morphisms. Importantly, between 2 fixed objects. So you need to have, it's not just that there's some infinite set of morphisms, that's easy, but an infinite set of morphisms between 2 fixed objects. That's the hard part. Okay. Well, the first thing is kind of silly. So we're assuming non-triviality, right? The trichotomy level we're on is non-trivial and locally modular. So we're non-trivial. So that means that there's some infinite family of plane curves. So let's just call it of plane curves. In fact, stationary non-trivial plane curves, but I'll just abbreviate as plane curves, xt and m squared. Okay, so we have those. Now those are kind of like bijections. So these are like they're close to being bijections from m to m, but they're not. Right? So these are sort of like approximate bijections. Because instead of having a 1-to-1 correspondence, each side, like each point goes to finitely many things on the other side. But this is the way we want to think, is they're approximate bijections. Now, there's a really cheap trick which just turns such a thing into a bijection. So let's just say we can do a sort of cheap thing, and then we have a bijection. So we're going to change m to a different thing on both the left and the right. So let's replace the right m with the collection of finite sets that appear. So the collection of xt of a for a and m. Right? So for each element a of m, if you look at where it goes to on the right, you get a finite set under xt. So xt is our correspondence. So little a corresponds to some finite set on the right, and we're going to replace m with the collection of all finite sets appearing in that way. And we'll call this zt. with ZT equals that collection. So now what we have is xt is been magically turned into a function. It's a function from m to zt. And it's a finite to one function. Okay. Well, great. And it's also definable. And it's definable in MEQ. It's definable in MEQ because you can talk about finite sets. So MEQ is a sufficient language to code a finite set. You just say like the set AB is the image of the ordered pair AB under quotienting by permutations, right? So you can view finite sets. It's like the finite sets. So here we can specifically say xt of A lives inside the symmetric kth power, right? The symmetric kth power equals m to the k mod permutations. And this is a sort in MEQ. So this is a definable thing. Okay. So now we have cheaply built a finite to one definable function, and well, in a just as cheap way, we turn it into a bijection. So now let zt, so let yt be the left copy of m mod, say, tilde, where you say that x tilde y if they go to the same place. Okay, so it's just we have a function. It's not injective. We want it to be injective, so you just mod by the equivalence relation of going to the same place. And now suddenly it's injective. So now xt going from yt to zt is a bijection. Okay, great. This is a completely cheap trick to turn a non-bijection into a bijection. So that's not very useful. So I mean, it's very useful because that goes into the main proof. But why doesn't it work? So the reason this doesn't work, so this is not enough. So what you could do is take a big family of curves, do this with each one, and say, well, now I have a family of bijections. So why is that not good enough? So this is not enough because we change the domain and range, so domain and codomain. So yt and zt vary with t. Right? And our goal is to come up with a infinite collection of morphisms from two fixed objects. So this is not enough. So we will show that after some tweaks, so after sort of manipulating M and replacing it with something else, we can arrange a special scenario where if you do this, the yt and zt don't change. That's what we'll do. We want to show that there's some special configuration situation where you do exactly this thing, and then these yt and zt don't change. So sort of what we're saying is that you're going to construct a family of curves where these equivalence relations of like having the same fiber on the other side don't change as you vary the parameter. And then that will be enough. Okay. Right. Now, key to doing this, so key idea throughout is going to be a composition of plane curves. So I can just tell you there's a direct definition of composition of plane curves. So if y and x are non-trivial plane curves, say stationary non-trivial plane curves, if you prefer to say stationary, then we can define y composed with x basically you just take the composition of functions, except they're not quite functions, they're curves. Right, so y composed with x is going to be the set of AC such that for some b, so we can't just say like y of x of, because it's not a function, but you just say for some b, AB is in x and BC is in y. Okay, so that's the composition, and then y composed with x is also a plane curve, so is a non-trivial plane curve. But the big problem here, and the thing that makes a lot of the complexity happen in this proof, is that it might not be stationary. Not always stationary. So if you compose two stationary things, you don't always get a stationary thing. Maybe I should have given that as an exercise, come up with an example of two stationary curves that compose to a non-stationary curve. Right. So what do we do? So in the end, we need to code composition into the language of types and canonical bases. And this is maybe stretches the it's one of the, it's a bit tricky to follow. I hope it'll be okay. I'm going to try to do it as sort of unintimidatingly as possible, but this is the idea, is we can't just talk about composition. We want to define a group where the operation is this composition, but we can't, because it's not going to, it doesn't produce a stationary curve, and that kind of breaks it. The calculus of canonical bases doesn't go through. So we need to do some sort of coding into types instead of taking curves. Okay, so I'll start this, and then we'll keep going after the break. So I'm just going to start. A first definition is what I'm going to call a non-trivial configuration. So there's going to be different configurations. The key word here is there's going to be configurations. And in abstract model theory, you see group configurations, right? And this for the same reason. You have to sort of code things into configurations of points. So a non-trivial configuration for me is, let me make sure I understand it, what I was going to say. Yes, is a triple. So it's exactly what happens if you're non-trivial. It's exactly the thing that has to exist if you're non-trivial. And it's going to look something like this. So is a tuple ABT in MEQ such that, well, what we want to say is that we have a family of curves, and we've chosen a generic curve in the family where T is the parameter for that curve, and then we take AB as a generic point. Okay, so the way it's going to look is that so dimension of T equals dimension of A equals dimension of B equals 1. Dimension of any two of them, AB, AT, BT, are all 2. A and B are interalgebraic over T. And T is the canonical base of AB over T. It's a non-trivial configuration. And if that looks confusing, the canonical example, because this is what I mean by we're taking a natural thing of just families of plane curves, and we're having to code it sort of awkwardly into the language of configurations of types, because we want a smooth way of doing composition. The canonical example is if xt is a one-dimensional faithful family of plane curves, family of non-trivial stationary plane curves, which is what exists if you're not locally modular, or sorry, which is what exists if you're non-trivial, then we just fix a generic T. So fix a generic T and then a generic AB from XT. And you get this configuration. All right, so when I say non-trivial configuration, think one-dimensional family of curves with a point chosen. So we've chosen a generic curve, that's our T, and then we choose a point over it, that's our AB. So the fact that A and B are interalgebraic over T is saying there is a curve defined over T, which has AB as a point on it. That's why they're interalgebraic. And I think it's an exercise to check. So check this example. And that's one of the exercises. I guess, yeah, I should stop for now.
All right, so yeah, now there's a half-hour break and we'll resume at 45 past the hour. Yeah, those are the only examples of non-trivial configurations, right?
Yeah.
Or in some sense, I guess it's like if the plane curve is coming from a product of two.
Yeah, the only difference is that I assumed A and B are just an MEQ, not that they're singletons. So
yeah, okay.
yeah.
This kind of configuration isn't the like usual group configuration, right? Because that one is like you have this sort of that one
Yes.
shape.
Yeah, so I'm gonna define something next called a composition configuration, and funnily that looks very much like a group configuration, and it turns out to be a group configuration because of some other facts, but it's like it's not assumed to be one, so the definition's different.
Oh, okay.
Well, the group configurations are, I think, less useful in the locally modular case because you can get a group configuration using local modularity, or you can just use local modularity. So it's like what I'm saying, you don't really need the full power of the group configuration theorem because you just use the local modularity instead of the group configuration property. So
yeah, okay.
Yeah. Okay. I'm gonna leave my sound on. I'll be around, but I'm gonna do a couple things and be back in like 20 minutes, but say something. I'll hear you if you talk, so.
Okay, you can get started now.
Okay, so to recap, so a non-trivial configuration represents a one-dimensional family of plane curves, and the translation is it's ABT. T is the parameter for a curve, AB is a point on the curve. I realized that I think the definition I gave is like very slightly different than the definition in the notes, but it's equivalent. There's all these properties and like a lot of them imply each other, so it's might accidentally omit one or add an extra or something like that. But the key point is just really that you have these 3 points. Any two of them are independent, but each one, the third one is algebraic over the other two. So any two are independent, but the three as a whole are not. Okay, so right, so non-trivial configuration. So analogy, non-trivial configuration goes with a one-dimensional family of curves. And now we'll do something called composition configuration. And that's going to go with the analogy there is going to be a composition of two one-dimensional families. Okay, so now the thing we're trying to encode is that we've got something like xt, which is a one-dimensional family of plane curves, and then we've got yu, which is another one-dimensional family of plane curves. And now out of those, we want to take the compositions, so the set of all things of the form yu composed with xt. But again, you can't just So this whole time since we're doing these canonical base, manipulations, we really need everything to be stationary, and those things are not stationary, which is kind of why we're doing it in this configuration sense. But we're going to capture this picture in a configuration. Okay, so here's the definition. So a composition configuration which this is basically what instability is called a group configuration, but I'm not actually going to write all the properties you need of a group configuration. I'm going to write the ones that are clear, and then the others kind of fall out of some other computations that we'll do later. For now, it's not correct to call it a group configuration, so I'm calling it a composition configuration. Where's my definition? It's a long enough definition. I really have to find it and copy. Here it is. So it's a tuple of 6 things. So a tuple, I'm going to write S. The whole tuple is going to, I'll call it S, and then it consists of points which are labeled as A1, A2, A3. And then it has a T's, so there's 3 T's, and the labels for the T's are 2 numbers, so 1, 2, T2, 3, and T1, 3. People in model theory label these 6 tuples like this in like so many different ways, and it honestly really annoys me because it's like someone will want to like permute them and think, oh, this role is supposed to be played by the 4th point, not the 5th point. And it's like this is like how I like to think of it. Okay. And these are all in MEQ, such that, and now we have a similar list of properties. But I'll draw a picture at the end. It should hopefully make it clear. So one is that A1, A2, T1, 2, and also A2, A3, A2, 3, sorry, T2, 3 should be non-trivial configurations. So I told you this is supposed to represent the composition of 2 families. And so we should begin with 2 non-trivial configurations because those represent families. So that's what those are. So these are non-trivial configurations, as I just defined. Okay. That tells you almost everything you need to know, except that only covers 5 of the 6 points. And so what's the 6th point? So we know that T1, 2, for instance, is the canonical base of A1, A2 over it. Like we know that 2 of the 3 T's are canonical bases. The last one, so T1, 3, is defined as the canonical base of A1, A3 over T1, 2, T2, 3. And if you think about it, that is supposed to be a composition. Like that collection of like points is supposed to represent composition. And then lastly is to make sure that it's sort of like a maximal generic composition. So you're composing all curves in the family, not just some. We make the dimension as large as it could possibly be from that assumption, which is 3. Okay, so the assumption that dimension is 3 is just saying there's no there's no dependence between these points other than the ones that have to be there. So in particular, notice that well, A1, A2, and T1, 2. So the first thing has dimension 2. And the second thing over that has dimension only 1 because you already have A2, and then say you add A3, and that gets you T2, 3. So like one of these 2 triples has a dimension of 2, the next one has a dimension of 1 over it. And then the final point, because it's a canonical base over the 2 T's that are already there, you already have that canonical base. That's algebraic over the rest. That can be checked, but I'm just saying there's no non-trivial dependencies. Okay, no, so where does this come from? So suppose we're in the situation above, so xt and yu are one-dimensional families of curves. So what are we doing? So we fix some t and u generic as possible. So we'll fix T and U generic where they're independent from each other. So in other words, TU is a generic pair, not just individually generic. It's a generic pair. And then we'll fix right. I didn't want to do that. Okay. This is okay. Right. We'll say okay. I can fix it. So we'll define. We'll start defining our configuration. So T12 is going to be our T, and then T23 is going to be U. So that's the first 2 points. So the first two T values are just a generic pair of curves, and then we take A1 to just be some generic in M over those. Okay. Now, because this X T12 is a plane curve, it's a finite correspondence, M to M, we can extend A1 to a point to make it on that one. So we take A2 in the image of A1 under XT. Yeah. And this is also generic in M over T1 to T13. And then we take A3 to be in the image of A2 under the second curve. Yeah. So it's like you have an A1, you map it over to an A2, and the thing you use to map it is T12, and then you map that to an A3, and the thing you use to map here is T23. Okay. Now, the last point is T2, so T13 is then going to just be the it's basically, it's not exactly, but it's basically going to be representing the composition of the two curves. But it's, again, it can't quite do that because the composition is not stationary. So what it really is T13 is a canonical base of one of the components. So this is really a component of the composition. And so T13 is what's going to take A1 to A3. Okay. So maybe a better picture is more like a triangle. So you have a see A1 maps to A2, maps to A3, and then the composition maps A1 to A3, and then you have a curve T12 doing this action, T23 doing this action, and then you have T13 doing this action. Okay, so this is the canonical composition configuration. Okay, and the idea is locus, if we take locus of A1, A3 over T12 and T23, this is a curve with A1, A3 as a generic point. So that's the relationship there. So it's just it's a configuration of points that represents a composition. Okay. So now what does local modularity have to do with this? So that's a composition configuration. That's a fundamental object we use. Now I want to say, what does local modularity tell you about such things? So quick little lemma. Oh, that would be skipping one. There's another lemma first. Okay, two lemmas. So two quick lemmas. And then one more weird lemma. So two easier lemmas about such things. Well, maybe not trivial. So lemma, I'm going to call this cancellation laws. If you think of this as being like a groupoid, like the T's are representing actual functions with composition, then this is clear, but just check it. So in such a configuration, each of the T's is algebraic over the other two. Is algebraic over the other two, yeah. Okay. I'm calling it cancellation law. It's like if you know a product of two things, then you can, if you know what the product is and you know one of the two factors is, then you know the other two factors. That's why it's a cancellation law. And I'll just sketch, right? So approximately why is this? Well, first of all, T13 is in ACL of T12, T23, because it's a canonical base of something which is defined over T12 and T23, right? So because T13 equals CB of a point over there. Now that's some like abstract way of saying it. Let's make it a little bit more explicit. So precisely or explicitly, let's fix X X to be some curve representing the locus of A1, A2 over T12. So X is like the first curve in the composition, and then Y is a curve representing the locus of A2, A3 over T2, T3, and then let's let Z be in the locus of A1, A3 over T13. Okay, so here's the three curves that we're going to the configuration, and without loss of generality, because these T's are the canonical bases, we can assume that they actually define the precise sets. So without loss of generality, X is T12 definable, and then similarly for the others. Yeah. Well then, precisely what happens is that Z is going to be well, almost contained in the composition Y composed with X. Right, and the reason we know that is because the reason we know that is because the point A1, A3 is generic in Z and belongs to the composition. It belongs to the composition because it's witnessed by A2. Right. And so what that means is that, well, Z is a component, it's a stationary component of the composition. And so that makes it the canonical base of Z is one of the finitely many canonical bases of components, and so it's algebraic because there's only finitely many. The ACL of the others. Okay, so this is the idea. You can, I mean, if there's more, if that doesn't satisfy you, I will leave the fully satisfying yourself with that as an exercise. That's one direction. The other two directions are very similar, but with a little bit of a twist. So Y is for example, T12 in ACL of T13 and T23. Well, now it's not a direct composition, but we're going to bring in a cancellation. So like inverting, taking the inverse off. This is because the T12 represents X, and X is a component of something else. I'm going to try to make sure I get this right. X is a component. Did I write it down so I make sure I get it right? X is a component of, oh, I wrote it down, but I did the other one of, I believe it's Y inverse Z. Yeah, of Y inverse composed with Z. All right, so Y inverse composed with Z, what that means is it's like the set of X, Y, so that for some Z, you get XZ in Z and YZ and Y. Okay, so it's a composition, but you have to cancel, you have to go backwards. Right, so it's saying you can express the individual pieces of a composition in terms of the other piece of the composition together with the full composition. It's cancellation law. And it's for a similar reason. So you can finish the details there. Right. So that's one relatively easy lemma, I hope. And then the second lemma is the application. What does local modularity tell us? Well, it tells us the following. Given such a configuration, the point T13, this last point that we added, the most confusing point, it has dimension at most 1. So again, that's what local modularity says. It's T13 is coding a curve inside the product of two strongly minimal sets, and such a thing has dimension at most 1. Okay. And it follows, in fact, it equals 1. In fact, it equals 1. And it follows that, in fact, there's a third non-trivial configuration. So A1, A3, T13, unsurprisingly, is a non-trivial configuration. Just because all the points have dimension 1, then I'm skipping like all of the computations, but I'm trusting you can do that. If you want to check all of the details that it's a non-trivial configuration, you can. Okay, but really the only non-trivial part of showing that it's a non-trivial configuration is computing the dimension of the t coordinate here. And it's 1 by local modularity. It's easy to see that it's at least 1. Maybe I'll write that down. So notice that dimension of T13 is at least as big as the dimension of, say, T13 over T12, because adding parameters only makes the dimension go down. Well, by the cancellation laws that we just proved, each of these 3 t values is algebraic of the other two. So in particular, dimension of T13 over T12 is the same as the dimension of T23 over T12. The other two t's are inner algebraic over the first one. And that's 1. That's 1 because T23 and T12 are independent. That's part of the assumptions of the composition configuration. So when I said that when I assumed that the dimension of the composition configuration was 3, there's one of these axioms that says the dimension is as big as possible, meaning there's no non-trivial relations, dependencies. Part of that is that the two curves you composed have to be independent. Okay, so that's why it's at least 1, and then it's at most 1, but also it's at most 1 by local modularity. Okay. Right. So right. Now this gets interesting. So I'm going to prove a lemma, and the lemma is going to make no sense at all. But it's just this is where this proof just gets like whoever would think to do this. So I'm going to call it the coordinate-wise inner algebricity lemma. So from now on, just to make things smoother. So from now on, I'm just going to use the notation. I'll say A tilde B to mean A and B are inner algebraic. Because there's going to be a whole lot of things being inner algebraic. So I'll just say A tilde B. That's what that means. So here's the lemma. And I'm just going to state it because there's just no motivation at all for this. So here's our coordinate-wise inner algebricity lemma. So suppose we have 2 composition configurations. I'm going to draw a picture of these things eventually. So two composition configurations whose t coordinates agree. So we have SA is what we've been doing. And then we have an SB, which have the same T's but different first parts, which are B's. Okay, so suppose these are both composition configurations. Okay, then if A1 is interalgebraic with B1 and A2 is interalgebraic with A3, then I'm sorry, with B2. Yeah. With B2. Okay, then A3 is interalgebraic with B3. Right? So if the first two are interalgebraic pairs, then so is the third. And then similarly for all permutations of 1, 2, 3. Okay, so if A1 is interalgebraic with B1 and A3 is interalgebraic with B3, then the same for A2 and B2. And then if A2, B2 are interalgebraic and so are A3, B3, then so is A1, B1. So if AI, BI are interalgebraic for two values of I, then they're interalgebraic for all values of I. That's the lemma. Where the basic motivation is that, remember, we're trying to find some situation where if you like mod out by the equivalence relation of having the same fiber, then like the resulting quotient doesn't vary. So we want the equivalence relation of having the same fiber to be like not varying. So what we're trying to kind of do is compute that equivalence relation. Right. So and so yes, we're these things having the same, being two composition configurations with the same T's are like saying they're in some same fibers, and we're trying to talk about the equivalence relation you get. That's pretty much all the motivation I can give for now. But so here's the picture: is that you have say A1 and B1. Okay, and then here you have A2 and B2, and then you have A3 and B3, and you have interalgebricity here and here. And then you have a curve which takes A1 to A2. Sorry, I won't write it that way. I'll write it this way. Okay, you have a curve which takes A1 to A2 and also takes B1 to B2. And then you have a curve here which takes A2 to A3 and also takes B2 to B3. And then you have a total curve like this, which takes A1 to A3 and it also takes B1 to B3. Okay, so here's a crazy proof. So suppose not. Okay, so proof. So suppose not. Okay, then dimension of A3, B3 is 2. Okay, because all of the points, all the A's and the B's and the T's, all these points are dimension 1 points. So you have 2 points, they each have dimension 1. Well, then either they're independent or they're interalgebraic. If they're not interalgebraic, then it has dimension 2. Right. So let's make some dimension computations. So let's compute the dimension of the right side. This is the right side. Everything on the right. So dimension of right side is what exactly? Well, we can start with the top right, which is a non-trivial configuration. So it's dimension of A2, A3, T23. Okay, plus the dimension of the other stuff over that, right? And we don't have to repeat the T23, so we can just add B2, B3 over that. Over that. Okay. Well, the first part is a non-trivial configuration, and those have dimension 2, all of them. So this is 2. Plus, what does B2, B3 look like over A2, A3, and T23? So in other words, if you just have this top stuff here, how much dimension are you adding to add to the bottom? Well, you're not adding any to get B2 because B2 and A2 are interalgebraic. So if you have A2, then you get B2 for free. But then you have a curve which takes B2 to B3, and so you actually get B3 for 3 as well. So starting from A2, you get to B2, and now using your T thing, you get from B2 to B3. So there's actually 2 plus 0, which is 2. So the whole right side of everything is 2. Well, that's the same as A3, B3, which is part of the right side, right? So what that means is that the right side is all in the ACL of A3, B3. In other words, the whole right side, by the additivity, the entire right side has to have dimension 0 over A3, B3, which means A3, B3 has to be enough to generate the entire right. Okay? Now, by similar reasoning, same argument, using the 1 to 3 part instead of the 2 to 3 part. So if I go back up here, what I really just did is I made some computation operating only in the 2 and 3 side. So now if I did the same computation but using 1 and 3, then everything I just said with the 2, I can replace it with the 1, and the same argument is going to be true. So we get that all 1, 3 points. So what do I mean by that? I mean A1, A3, B1, B3, T1, 3. All of that is also algebraic over just A3, B3. And I know this makes absolutely no sense. Like you have no idea where this is going. And it just has to be that way for a little bit. Okay, so looking back at the original configuration here, so I have just these right 2 points. And these right 2 points are enough to generate, they're enough to generate everything in this right box. And also, they're enough to generate this much. And all that's left is T1, 2. But we also actually have T1, 2 as well. Why do we have T1, 2? Because we have T1, 3 and we have T2, 3. And we just proved this cancellation lemma that if you have 2 of the T's, then you have the third. So, in fact, this means that the last point that we have not yet addressed is also in, because it's in ACL of T1, 3, T2, 3, which is also contained in the ACL of A3, B3. Okay. So what do we just show? We have shown that all points in the entire diagram, SA, SB, the entire thing is contained in the ACL of just A3 and B3. That cannot be. This is a contradiction. Why is it a contradiction? Because, well, the dimension of SA is 3. It's a composition configuration, so it has a dimension of 3. And that's bigger than the dimension of A3, B3. So a two-dimensional tuple can't see a three-dimensional tuple. Okay, so that's it. That's my incredibly unmotivated lemma. Any questions about that?
Yeah, I have a question, though maybe it's only interesting to me. So this proof really depended on the fact that everything was in the one-dimensional case. Does you have to use the fact that, or it seemed like the way you're counting dimensions depends on this being one-dimensional, but is it correct that there's also a version of this that would work there's a version of this for like the general group configuration, right?
Yeah.
I have some memory about this.
Yeah, there's a version that works. It's just that you still show that like so instead of getting that the whole thing is algebraic over A3 B3, like say you're doing the two-dimensional group configuration, you would get that the whole right side has dimension 1 over A3 B3 when you would expect it as dimension 2 over A3 B3. So you still get something where like all like the various pieces have smaller than expected dimensions over A3 B3, and then you add them all up, and then you get that the whole thing has dimension that's too small.
Okay.
Yeah, and like I said, I took this argument out of Pile's geometric stability theory book, and he's doing it in the two-dimensional case. So what you're seeing here is his argument, which looked like that, but adapted to the one-dimensional case. Okay. So now we can prove something. So theorem. There are objects in our groupoid C and D, and a morphism F from C to D with dimension of F over CD equal 1. And this is what we've been wanting, right? This is there exists, so that means there exists a family, an infinite family of morphisms at a point. So at two objects. Okay, that's what we want. Okay. So let's get into that. And I hope you'll see that this crazy weird lemma above is the key to proving this. Okay, so the first thing is we're just going to fix a one-dimensional family of curves. So we fix xt, t and t. I'll use that notation. A faithful, let's say, one-dimensional family of curves. But what I really mean, really deep down, what I really mean is we just fix a non-trivial configuration. But I mean, it's easier to think of it as we fix a family of curves. So how do we know that this exists? Well, non-triviality gives you that you can have a one-dimensional family. Local modularity gives you that you can't have any bigger than a one-dimensional family, so you have to have exactly a one-dimensional family. So we fix such a thing. So that's the assumption underlying the whole thing is non-trivial locally modular. Right, and now we're going to take two generic members of the family. So it's like we're setting up this composition configuration. So we fix T and U, a generic pair of curves. Right. And now I'm just going to say fill in the following diagram. And I'm just going to draw a picture. I'm not going to define all the points successfully. I just draw the diagram. So we have, what do I call them in the proof? I call them A, B, and C. Good. So I have A going to a point B using the curve T. Then I have that going to a point C using the curve U. And then that will go to a point D using the curve T again. Okay, so this is the diagram. You go T and then U and then T. So there are two, so we have two composition configurations present here. Right, we have the left one and the right one. So, and I think I called them S left equals ABC T U V, and S right is BCD UTW. Now I just said V and W and I hadn't defined those, but they follow out of what a composition configuration is. So there has to be some curve which sends A straight to C, and we're calling that V. And then there's a curve that sends B straight to D, and we're calling that W. So this is filling in the details of the composition configuration definition. So here V precisely is the canonical base of AC over TU. W is the canonical base of BD over UT. We're just saying V is the curve that is like a composition of T and U, and then W is a curve that's a composition of U and T. Okay. Right. So that's the setup, and now what do we want to do is it's going to be a bit of a curveball here. So instead, we're now going to replace M with the T curve. So we will, the idea is we think of replace M so normally we think of curves as acting on M, plane curves act on M. We're no longer going to do that. We're going to think of curves as acting on XT. So replace M with XT, the T curve. Okay. And in particular, this means that we're going to think of T as fixed. This means, so think of T is now fixed. And we think of U as varying. Okay, and we think of XU, so our curve, our U curve, as acting on XT. So what I mean by that is we've got 2 points in XT. So we have a first point in XT, which is AB. We have a second point, which is CD. So we have XU sends AB to CD here. Right, so I have on the left side, I have a point in XT. On the right side, I have a point in XT. And there's a definable way of getting from this left point to the right point, which is by applying this U curve. So precisely, okay, more generally, so precisely view XU as defining a curve, a plane curve, but now in XT squared, not in M squared, but in XT squared. And the definition is, and I'll call it, I gave it a name, right? Did I give it a name? Yes, the name was WU. Okay, so X2 is defining a curve, which I'm going to call WU. Okay, WU in XT squared. And the definition is just that, so say I have a point XY and a point ZW, these are in XT, then I call the pair XYZW to be in WU if YZ, so if these two middle points are in XU. Okay, so I have a way of taking one point from XT and mapping it to another point from XT by linking the two coordinates that are next to each other through the curve XU.
Is that stationary?
No, WU is not. But we're going to turn it into something that is. And of course it might be, but it's probably not. Might not be. Okay. So now we have our WU. Okay, and in particular, so we have a family of things of the form, say W U prime, right? For all the U primes. So we can fix T, we can fix our XT and then take collection of all of these WUs for U varying. And now we're going to show that if you take that collection of WUs and you do the tricks we did before to turn them all into bijections, that the bijections all go between the same two sets. Okay. So, okay. So let's start that. Right. So we do the same thing before. So we view WU as a bijection from a set. What did I call them here? What did I call them? YU to ZU. As before. So what does that mean? ZU is the collection of images WU applied to some X bar, where X bar is in XT. And here we view this image as an element of a symmetric power, XT symmetric power K. For some K, that's just XT to the K mod permutations, and that's an MEQ. So that's a definable thing. And so then this gives a way to view WU as a function from XT to this ZU. And then we just let YU be XT mod the relation by mod the same fiber relation, fiber equivalence relation. Okay, and then we call the resulting thing. So call the result FU, which goes from YU to ZU. And this is now a bijection. And it's definable. It's definable in a uniform way from the original collection of XUs. Each XU turns into the bijection FU from YU to ZU, definably in a uniform way. Right. There's something else I wanted to say about that for now. Oh, yes, there is something else I wanted to say about that for now. So note, or maybe I should just say check, but I'll just say note that YU and ZU are strongly minimal as well. Yeah, I guess you can check that. So why first of all, ZU is strongly minimal. The reason ZU is strongly minimal is because you have this function here, WU going from a strongly minimal set XT to ZU. An image of a strongly minimal set under a function, as long as it's infinite, it's still strongly minimal. That you can check, because if the image split into two pieces, then the pre-images of the two pieces would split the domain. And so images of strongly minimal sets are still strongly minimal. And then YU is in bijection with ZU, so it's still strongly minimal as well. And so we've we've reduced to two strongly minimalist things, and so we can view FU as, at least the class of it, is a morphism from the class of YU to the class of ZU in our germ groupoid. We've just produced a morphism. Okay. So FU, yeah, I think in the notes, what I really did in the notes, not that this matters that much, but I was still calling it WU here. And then I started calling it FU once it was a morphism. So FU is actually an almost equality class to be official, but that shouldn't really change anything. Okay, so now what's the key point? So the point is that the class of YU and ZU don't depend on you. So canonical base of YU is algebraic over T, and similarly the canonical base of ZU is algebraic over T. This is our way of saying they don't depend on you. In other words, if you have fixed T and you vary these other things in a family, the YU and the ZU, you vary them as a family, the almost equality class doesn't actually change. It stays between the same finitely many values. Right. Okay. So let's do that. This is going to be I'm probably going to like not know what I'm doing at some point in the near future. I'm okay so far. I don't trust myself that much longer. Right. So let's go back to our original configuration. Maybe I'll draw the configuration again. We had some points here. So we had A, B, we had A and B, which were on our T curve, and then we have C and D are on our T curve, and they are linked this way by U. Yeah, that was our picture. So let's think about what are the other things. So AB, yeah, let's look at where AB goes. Okay, so let H be the image of AB under WU. Okay, so I'm taking my first point here, AB, and I'm looking at what's its image under passing through the U curve. Well, that's an element of ZU. And it's in fact generic in ZU over TU. Okay, why? Because by the way I built these things, AB is generic in XT over TU. And then, well, so H is just like infinite correspondence with T. It's interalgebraic. So AB is interalgebraic with H. And I'll put TU there to denote that's over the parameter set TU. Okay, so this H has dimension 1 over TU. It's a generic point of ZU over TU. All right, now H is a finite set, and so what we want to do is what are the other things that are in H? So one thing that's in H, so note that our other point CD from our configuration is definitely in H. H is a finite set, so CD is in H because it goes with AB. That's in our diagram. Well, what are the other things? So if we have another point, C prime D prime in H, what can we say about C prime D prime? Well, this is where we go back to the unmotivated lemma. So if C prime D prime is in H, let me draw the picture, is we have A, B, C, D, and then we have another analogous diagram with C prime and D prime. and we have our linking T, U, T throughout the whole thing. Okay. Remember, our unmotivated lemma says that if you have like one configuration stacked on top of another, and if two of the vertical lines are inner algebraic pairs, then so is the third. So we have certainly on the left, the two things are inner algebraic. It's A with itself. And then, of course, B and B are inner algebraic. So therefore, C and C prime are inner algebraic. So then, by the unmotivated lemma, C and C prime are inner algebraic. Okay, but then do the same thing on the right side, right? So the first time I just did in the left configuration, now do it in the right configuration, and you get the D and D prime. So also D and D prime are inner algebraic. Okay? And in particular, C prime D prime is inner algebraic with CD. So H is a finite set of points, but it's not that crazy of a finite set of points because all the points in H are inner algebraic with each other. So this means in particular that H as a whole set is just inner algebraic with our original CD. It's a finite list of things and they're all inner algebraic with CD, and the result is still inner algebraic with CD. Okay. Now we'll go back the other way. All right, now I have to read what I did again. Yeah, right. So now we do the same argument in reverse. So now let's let G be the preimage of H. So WU inverse of H. Everything in YU, so everything that ultimately maps to ZU. Then similarly, by going from right to left, so same argument in reverse, any two elements of H. So elements of G are inner algebraic. And this means that G is just inner algebraic with AB. Yeah, so AB was one element of G, and then all the others are just inner algebraic. Okay. Crazy, right? So, right. So that's really it. That's really the trick, is that we have these, originally we had XT on the left and XT on the right, and then we did some manipulation to get a bijection, but we didn't manipulate it that far because the resulting points on the right and the left were just inner algebraic with the originals. That's the key point. Okay, so now how do we finish this? Well, now, so what is the canonical base? So let's say that, so now, okay, the dimension of canonical base of Z, U, no, let's just do YU. So we're interested in the, okay. Let's name these things. Okay, so I gave these specific names in the notes, so I'm going to do that again here. So let P be canonical base of our YU, and Q canonical base of ZU, and R canonical base of the function going between them. Okay, so P, Q, and R are the three things that we're going to look at. So, well, we want to know something about dimension of R. Did I? Okay. Of course. Okay. What am I doing? What am I doing? No. I told you I would lose what I was doing at some point. Okay, I told you that the goal I was trying to say that CB of YU and CB of ZU are just algebraic over T. That's what I'm trying to say. Well, why is that? So the dimension of CB of YU over T. Okay, what is that? YU is just YU, one generic element of YU is G. So this is dimension of CB of G over TU. Because the locus of G over TU is actually just YU. It's a generic element there. But G is interalgebraic with AB. So it's actually a valid maneuver, and maybe I'm skipping, I didn't tell you why this is a valid maneuver, but it's not that hard to check. You can replace things that are interalgebraic here. So this is AB. It's the same as AB because G is interalgebraic with AB. So interalgebraic tuples have interalgebraic canonical bases. I think that's an exercise somewhere. So I'll say exercise. In general, X is interalgebraic with Y over a set A implies that so are their canonical bases. Okay. Okay, so the dimension of CB of YU over T can be traced back to the dimension of the CB of AB over TU. Okay, but what is that? Well, AB is a generic point of our original curve XT over TU. So that's just XT, right? So so this is just dimension of CB of XT over T. And this is because AB is in XT and it's generic over TU. That was by construction. So the canonical, so the locus of AB over TU is just the set XT. Okay, well, what's the canonical base of XT? It's T. So it's the dimension of T over T, which is 0. Okay. So we have shown here that the canonical base of YU is in ACL of T, and same argument for ZU. Just using the other tuples on the other side instead. Whew, okay. And so that's it. So that's saying that if we turn our curve into a bijection, then the two sets it's a bijection between don't actually change. Like they're always the same two sets, basically. Now let's be formal. So now to formalize this, and we're trying to prove a theorem that I stated forever ago. The theorem is that there exists a morphism which has dimension 1 over its objects. So let's name the things, the actual elements of the groupoid. So let P be canonical base of YU, and let Q be canonical base of ZU. So what I said before I erased it, and then R is canonical base of the function between them. Right. Right. So we know that dimension of R over PQ is at most 1. This is what we said before by local modularity. And we want to know it's exactly 1. So toward the contrary, assume that it's 0. What would that look like? Okay. Right. Well, then that would imply that R, because R is an ACL of PQ, by assumption, if that's 0, R is an ACL of PQ, P and Q are both algebraic over T, right? So R is in ACL of T. So that would mean that our function, FU, is the canonical base is algebraic over T. So that would mean that in addition, the function doesn't even change. Okay? And that's going to be too much because basically the original curves do change, and that's going to make the function change. So how? But well, the dimension of GH over R is 1. What am I saying here? So R as a function, so FU sends G to H. And this is a generic point on the graph of FU. Right? So the dimension of GH over R is equal to 1. And this will mean that the dimension of GH over T is at most 1. Because R is algebraic over T. So T is like stronger data than R. Okay, so if you add more, then the dimension can only go down. And now if we compute, well, okay, and in particular, because of the interalgebricity, the dimension of AB over T is at most 1. And that's really what I was going for. That's not true. It's the dimension of AB over T is 2. If we want to verify that directly, what we could do is say, then dimension of I'm confused about what
You want to say that AB already is one dimensional. You want to say ABCD or something has dimension 2?
Oh, of course. Okay. G. Yeah. Oh, sorry. Thank you. Yeah. So G. Thank you. You saved me. So G, G is interalgebraic with A, B, and H is interalgebraic with C, D. So if this thing is less than 1, then what it really says is that A, B, C, D over T is less than or equal to 1. And that's not going to be true because that's going to imply that the entire configuration was too small. Okay, so in particular, what that means is that the dimension of ABCT is at most 2. Why? Because T is at most 1 by local modularity. T was originally a curve from a one-dimensional family, and then ABC over it can be at most 1, and combined you get at most 2. Right, but the whole left side is in the ACL of that. So this is, again, forever ago. Here was our diagram. If you're given A, B, C, and T, then from B and C, you can get U. From T and U, you can get V. And you have an entire composition configuration. And dimension of the whole configuration has to be 3, and that's a contradiction. Okay, the last page probably was quite confusing, but what it's saying really is that the two sets that you have a bijection between don't change. That's what it means to say that the canonical bases of the YU and ZU are algebraic over T. It's just saying the sets that you have a bijection between don't change as you vary U. And originally you had a one-dimensional family of curves. It's going to stay as a one-dimensional family of things. Okay, you can't have a one-dimensional family of curves that collapses to a zero-dimensional family after only modding by a finite equivalence relation. That's basically what that says. Okay, so this proves our theorem that there is a family of curves. And as I told you, I still don't fully understand everything that just happened. I've seen it a bunch of times. It gets me every time. So, any questions about it? So this was by far the hardest part of building a group. So this is like the most difficult thing we have to do of the week is done. Let's maybe we can just start building a group because it's not that much of a stretch to build a group from here. We're not going to finish, but we'll finish next time. So let's fix. So now part 2, build a group. So we've proven that this family exists. So let's fix objects C and D. And well, we have a morphism of dimension 1 over CD. And what that really means is there's an infinite family of definable family of morphisms. And so what I'm going to do is I'm not going to take the morphism anymore. I'm just going to take the family and an infinite definable family F. I believe capital F is what I called it. Yes. Of morphisms from C to D in our group weight. Okay, and well, the dimension of F has to be at most 1 by local modularity. And it's infinite, so therefore it equals 1. And I'm not going to care about parameters that much anymore. Let's just take a stationary component of F and not worry about what it's defined over. So replace with a component. Which means that we may assume F is strongly minimal. Okay, so I have now a strongly minimal definable collection of morphisms between 2 objects. Okay. And from now on, so now that I've done that, from now on, I'm going to pretend. So from now on, we assume that these are all 0 definable. I'm just saying add constants, and then at the end of the day, we'll still have an interpretable group even if we take away the constants. It's fine. So the group will be interpreted over extra parameters anyway, so it's harmless to do that. Okay, so now what do we do? Well, we have a collection of maps. Now, unfortunately, they go between 2 different objects, and we want them to go from an object to itself. So what we're going to do is just we will build a family of compositions. And the compositions are going to go from C to D and back to C. And we're going to choose it in such a way that it's a group. That's the family of compositions. You have to be a little bit careful in how you do this. So the first instinct that I have is to say we have, okay, infinitely many ways of going from C to D. Now let's fix one map from D back to C. And then let's compose all of our C to D maps with the inverse of the 1 to get a family of maps from C to C. It's perfectly fine. You can do that, and it'll get you an infinite family of maps from C to C, but they won't form a group. What they'll form is a group up to finitely many error points. And we sort of want to avoid that. So we have to be a little bit careful. Yeah, I'll tell you the definition. I have some like couple of paragraphs about like here's some reasons that some things you might be tempted to try don't work here in the notes. Let me just give you the definition. So we define, because we're running out of time. So we'll define G in the following way. So I'm trying to pick out exactly which compositions C to D and back to C are good enough compositions to be included in a group. That's what I'm trying to do. Okay, to be the set of all morphisms from C to C expressible as a composition GH for as a composition GH inverse, where G and H are from our family, Okay, so as it stands, all I've written is take all compositions of go from C to D and then back to C. That's not good enough either. So, roughly speaking, the first thing I said, you won't get enough morphisms to have a group. If you take all compositions of all things from the family and all things from the family combined, you'll have too many morphisms, and so you have to do something in between. And so the trick is to say in infinitely many ways. Okay, so G is the set of morphisms of the form start from C, go to D, go to D by some, oh no. Wait, this is okay, right? Yeah, okay, go to D by some, no, it's not okay. I should have said G inverse H, I believe, if I'm drawing the picture this way. Yeah, I don't, you get the idea. So start from C, go to D by some map in our family, go back to C by another map in our family. Okay. And you get a morphism from C to C, but only keep only those F having infinitely many such expressions. Okay. And then it will turn out, so we will show tomorrow. So clearly, well, okay, by definability of being infinite or finite, by definability of dimension, G is definable. G is a definable collection of morphisms from C to C, and we will show that G is a group. And we will also show that it's strongly minimal. And we will do all that tomorrow. Okay, so I'm done for today.
Okay, so let's first thank Ben for today's talk. Okay, and then are there any questions? I had a question that was maybe extremely technical in the proof, in the really hard proof from today.
Yeah.
You take this composition that's like first do T, then do U, then do T. And this is somehow like using the fact that the domain of U, like the range of U is like the same as the domain of T, because these are all maps from like M to M.
Yeah.
And they're like general group configuration theorem, the sort of this like the two maps all like there's sort of three different places where the points live. And one, you have like a map from object A to object B and a map from object B to object C or something, and the domains don't line up. So is there like some different way to get this picture?
Yeah, okay. So what I would say, that's a good point. What I would say, the way that I think of it is you first convert to a group configuration where three of the points all have the same type.
Oh yeah, I guess you could do that.
Yeah, and it's basically like you just fix one of the points and then you take, instead of having a map that goes from one type to another type, you have it go there and back. And then you sort of check that all the inner algebraicities stay the same. And then yeah, you get that all the types are the same, and then you just mimic from there.
Okay.
I don't know if that's actually how it's usually done.
I remember I have a vague sense in like Pele's book in the like general proof, he does something weird where he sort of like takes this group configuration thing and like flips it, that like looks kind of like this, right? And then he like flips it over one side and like there's like some sort of three-dimensional picture, and
yeah.
Weird and like yeah, and then maybe it's the same picture, but it's hard to tell. I would have to like sit and think for a long time.
Yeah, I mean, I don't remember exactly what he does, but I do remember. So after I made sense of this version of the argument, I had looked at it a little bit and was like, yeah, the key things he's using seem to be the same thing as the key things I'm using. And just doing it without dimension. And so I kind of thought it seems to be the same argument, but I agree that it's not nearly as easy in the
Yeah.
not that this was easy, this was really hard. It's harder there when you don't have dimensions to work with.
Well, if there aren't any other questions, then I guess that's it for today. And there's still the section at 6:30 p.m. I think. I guess it's in person today because the weather got better. Is that right? Yeah. Okay, so that's it. I guess we can thank Ben again for today's.
Okay, thanks.
And,
Yeah,
yeah.
see you
Tomorrow.
everyone tomorrow. Yeah.